Hello, my name is Erin McCormick, and I will be discussing a project with Leslie Blaha and Cody Gonzalez titled Exploring Dynamic Decision-Making Strategies with Recurrence Quantification Analysis. The quick summary is that our project demonstrates how a visual analytics tool called Recurrence Quantification Analysis can provide new insights into patterns of dynamic decision-making. These insights augment traditional aggregate measures of behavior and raise questions, for future work, about the ability of existing theories to predict and explain the choice patterns that we observe using RQA. In more detail, many research projects use aggregate measures of behavior, choice proportions, total points, maximizing rates, even when we are studying ordered choice sequences where ultimately we are interested in the patterns seen within these sequences. In order to avoid obscuring these patterns in our present analysis, we used Recurrence Quantification Analysis, or RQA. RQA is an approach composed of recurrence plots and recurrence statistics. RQA was developed in physics to study complex systems and time series data, but has seen limited use in psychological and behavioral research so far. The foundation of this analysis is tracking recurrence, whether a particular event repeats in a sequence. In this equation, you can see how recurrence is calculated for a set of discrete event states, for example, whether a participant chose option A or option B. If we calculate R for every pairwise combination of time points in a given choice sequence, we can visualize recurrence in that sequence. For example, see Figure 1, the recurrence plot for behavior in a two-alternative forced choice task. Recurrence plots have 4 building blocks of interest: recurrence points, diagonal lines, vertical lines, and blocks of recurrence. We use these features to interpret the plots and study the underlying behavior in our dataset. The data that we analyze with RQA comes from a pre-existing experiment studying how different features of a dynamic choice environment affect how well decision-makers adapt to that environment. We used data from one condition, where participants made 100 repeated choices between 2 risky options. One of these options changed in expected value over time, and participants were paid a bonus for how many points they acquired in the experiment. Therefore, to get a higher bonus, participants needed to adapt to the change in expected value by choosing the stationary option in the first 49 trials, and then switching to the non-stationary option after trial 50. Thus, the recurrence plot for an optimal decision maker looks like Figure 4, where the first 49 trials are a repeated sequence of the stationary choice event state. Then, the remaining trials are a repeated sequence of the non-stationary choice event state. Our paper and poster provide the full quilt of recurrence plots for our data in Figure 5, and the distribution of the recurrence statistics in this sample in Figure 6. Here, I want to focus on 3 specific recurrence plots that illustrate one insight from this analysis. Figure 8 shows the recurrence plots for 4 participants, 3 of which have the highest maximization rates over all 100 trials. We can see patterns similar to the optimal choice pattern in all 3 recurrence plots, or RPs. Notably, we can also see variation in how they made their adaptive decisions, especially with regard to switches between the options, which may be particularly interesting for studies of exploratory behavior. Recurrence Plot 101 has little switching behavior in the beginning and a lot of consecutive choices, first choosing the stationary option and then mostly choosing the non-stationary option after trial 50. We can also see that 101's switch from stationary to non-stationary was not preceded by checking the current expected value of the non-stationary option, which we do see in 99. So 99 and 98, in contrast to 101, have more frequent switching rates during half of the task, but they also diverge on which half. 99 frequently switches before the expected value change, whereas 98 frequently switches after the expected value change. These plots and their associated statistics suggest that there are distinct patterns of trial-to-trial switches even among participants who are similarly categorized on aggregate measures. This raises questions about where these patterns come from. Are they explained by differences in experience outcomes, or perhaps by individual differences? This also raises questions about whether existing computational models of dynamic decision-making will reflect the variation we see here in human data, when assessed using an RQA approach. Our use of RQA has also suggested a rich set of possibilities for using this type of analysis. RQA was developed for any ordered sequence of observations, whether discrete or continuous. Thus, RQA can be used for human data or model-simulated choice sequences, from 2 alternative forced choice tasks to any number of choice options, and from auto-recurrence to cross-recurrence. Specifically, cross-recurrence assesses 2 different time series: 2 people completing the same task, for example, a game theoretic setting, a person, a computational model completing the same task, or 2 models compared to each other. In conclusion, we find that RQA reveals systematic variation among decision-makers who would be categorized similarly with aggregate measures. This implies RQA can give us new insights to assess and refine existing computational models and theories to better understand choice in dynamic environments. Thank you for listening. For more details, please see our paper and poster or contact us.